Alright, so in this video I'm going to be looking at the applied physics section of the Unit 5 exam in June 2010. Alright, so let's make a start. So we've got a playground roundabout that has a moment of inertia about its vertical axis of rotation of 82 kg/meters squared. We've got two children on it and it's going 35 revolutions per minute. We're going to model the children's point masses with the masses given, and we've got the distances. So we want to calculate the total moment of inertia of the roundabout, but including the children. So the first key thing to realise is that you've been given the moment of inertia of the roundabout, and you've got the mass and the distance of the two children. So to get the total moment of inertia, what we're going to do is add the moment of inertia of the roundabout plus the moment of inertia of the 39 kilogram child and the moment of inertia of the 28 kilogram child. So what we need to do is essentially add them all together. So we've got this one, and if we look up it was 82. And then we need to take the mass and the radius squared, so the 39 is going to be 39 times by 0.9 squared plus 28 times by 0.5 squared. So essentially we're adding together their moment of inertia. Where's my calculator? Here we go. So we've got 39 times 0.9 squared plus 28 times 0.5 squared plus 82, and when we put this together what we end up with is 120.59, which we're going to give as two symmetric figures, so we're going to give it as 1.2 times 10 to the 2 kilogram meter squared, because all the information in the question is two significant figures as well. Okay, calculate the total rotational kinetic energy of the roundabout and children. So in terms of the kinetic energy, it's going to be half I omega squared. So it's going to be half times 120 point, I think it was 59, times by, and we need to pick up the angular speed, which is given in revolutions per minute, so it's going to be 35, which gives you the number of revolutions, times by 2 pi to give you the number of radians, and then divide by 60 to give you the number of radians per second, and we'll square that, so it's 35 times 2 times pi, divided by 60, and it's squared, it's 120.59, divided by 2 gives you, what's that, 809.98, blah blah blah. So that's going to be 8.1 times 10 to the 2 joules there. I think if you use rounded answers you'd get more like 8.2, but you should, when you're using unrounded, get 8.1. Okay, so the children move closer to the centre of the roundabout so that they are both a distance of 0.36 from the centre. This changes total moment of inertia to 91 kg/meters squared. Explain why the roundabout speed changes as you move towards the centre of the roundabout. So we know that the angular momentum must be conserved, so that essentially angular momentum before equals angular momentum after, because no external force is acted. So we've got the principle behind this is conserve angular momentum. So angular momentum is I omega. So if the moment of inertia is going to decrease because it's gone from, I think, 120 to 91, So if I has decreased, to keep L the same, the angular speed must increase. Obviously for this you should write this out in words, but I don't have enough space on my screen to do that. But that's the general principle that you've got there. Okay, so calculate the new angular speed, assuming there is zero frictional torque or essentially no external torque acting. So angular momentum is going to be I omega. So omega 1, let's have a look. What did we have there? I'm just going to get that back up so I can have a look at the actual question itself. So we had an angular speed of 35 RPM. So let's go through the same process as before. We know that I1 was 120.59, and we know that I2 is 91. So if we want to get the new angular speed, it's going to be I1 omega 1 over I2. So that's going to be 120.59 times by 35 2 pi over 60, all divided by 91. So let's type that in. 120.59 times by 35 times by 2 times by pi, divided by 60, and then we divide that by 91, and that gives us an answer of 4.856 blah blah blah. So that's going to be 4.9 once you round it to two significant figures. And it wants us to calculate the new rotational kinetic energy. So we used this before, half I omega squared. It's going to be half times by 91 times by 4.85 yada 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 squared, and that comes out as, so let's square that answer from the previous question, times by 91 divided by 2 gives you 1073.35 dot dot dot, and so that would be 3 joules to three significant figures, but it's 1.703 would be the unrounded answer. Okay, so let's last question. Explain where the increase in rotational kinetic energy of the roundabout and the children has come from. So essentially, it told you that, I think it was up here, that the children are moving closer to the centre of the roundabout. So what they're going to be doing is they're doing work. So that's where the energy has come from. Obviously, energy always has to be conserved. And so that's why you're getting an increase in rotational kinetic energy, because you're doing work or transferring that work into the kinetic energy. So as they move closer to the centre, they'll be doing work, and that's where your energy comes from. Okay, so a grinding wheel is used to sharpen chisels in a school workshop. The chisel is forced against the edge of a grinding wheel so that the tangential force on the wheel is 7.0 newtons as the wheel rotates at 120 radians per second. The diameter of the grinding wheel is 0.15 meters. Calculate the torque. So torque is force times the distance from its centre of rotation. So that's going to be 7.0 times by 0.15 over 2. And so let's type that in. 7.0 times 0.15 divided by 2 gives you 0.525 meters, or 0.53, giving it like rounded to the correct number of significant figures. And it's the unit of torque, so that's going to be Newton meters, because we're multiplying a force by a distance. Calculate the power required to keep the wheel rotating at 120 radians per second. So power is the torque times the angular speed. So that's going to be 0.525 times 120. So let's multiply that answer by 120, which gives you 63 watts. I think if you use the 0.53 from the previous question, you get 64, but using unrounded you should get 63. When the chisel is removed and the motor is switched off, it takes 6.2 seconds for the wheel to come to rest. Calculate the number of rotations the grinding wheel makes in that time. So essentially, what have we got? We've got the torque. Do we have the moment of inertia somewhere? Nope, so we can't be using that one. Okay, so what we're trying to find is the angular displacement. We have the time, we have the initial angular speed, and we have the final angular speed, but we don't have any mechanism to find your angular acceleration. So what we're going to be using is t, and so the initial angular speed is 120, the final is 0, and it takes 6.2 seconds to come to rest. So let's first of all calculate that. 120 divided by 2 and 6.2 gives you 372 radians. So we'll divide that by 2 pi to give you the number of revolutions, and that's going to be 59. So that there is equal to 372 radians, and to go from radians to revolutions you divide by 2 pi, and that comes out as 59.20, or let's give that to 59.22 significant figures, because we're giving it as revolutions. Alright, so move on. Coefficient of performance of a refrigerator is given by coefficient of performance of the refrigerator is Q out. So Q out is the heat extracted from the fridge, so it's the heat out, and then Q in is the heat given into the surroundings here. So Q in is going to be the heat delivered into the surrounding. Into your hot sauce. And then your Q out for refrigerator, heat removed from the fridge, or from the food itself inside the fridge. That's what those two terms mean. The refrigerator is designed to make ice at -10 degrees Celsius from water initially at room temperature. The energy needed to make 1 kilogram of ice at -10 from water initially at room temperature is 420 kilojoules. The refrigerator has a coefficient of performance of 4.5. Calculate the input power if it was required to make 5.5 kilograms of ice every hour. So first of all, the energy that needs to be removed per hour is going to be this. And if we want the energy per second, or the power, essentially, this is going to be the amount of energy removed from it, so the power removed from your fridge before we calculate the amount of work. So 420 times 10 to the 3 times 5.5 divided by 60 times 60 gives you a power of 641.1.6 yada yada watts. But that's the heat removed, that's not the work put into the refrigerator. So we divide that by 4.5, that tells you the work that you've actually put into your refrigerator. Work per second in is going to be the power divided by the coefficient of performance, which is 4.5, which is going to give you 142.529 1.4 times 10 to the 2 watts, essentially, of power that you're actually putting in, or the work you're delivering in. Calculate the rate at which energy is delivered to the surroundings. So we need to work essentially what the P out is. So using the first law of thermodynamics, we know that's going to be P in plus W. So that's going to be 641.6 plus 142.592, which is going to be, let's put that into the calculator, 5.5 divided by 60. And we put those in and we end up with 784.259, which is going to be 7.8 times 10 to 2 watts going in there. Okay, let's move on. So we've got a model rocket for demonstrating the principle of rocket propulsion. Air is pumped into an upside down plastic bottle that has been partly filled with water. When the pressure reaches 3.6 times 10 to the 5, or 2.6 10 to the 5 above atmospheric pressure, the air valve is forced out by the water pressure and the air in the bottle expands. The expanding air forces water out of the neck of the bottle at high speed. This provides the thrust that lifts it into the air. The graph shows how the variation of pressure with volume for the air initially in the bottle as it expands from 3.6 to atmospheric pressure, assuming the expansion is adiabatic. Got it. Okay, so I'm just going to put this graph up on my computer because I can't see 2 pages at once. Okay, use the graph to estimate the work done by the air as it expands from a pressure of 3.6 to the atmospheric pressure. So anytime you're looking for a work done, that's going to be the area under the graph. So if we look at the graph, so we can actually count the squares for the area under the graph. The important thing is you don't go down to the x-axis, you only go down as the lowest point in the cycle, so when it reaches atmospheric pressure. So essentially you're looking at only a small section of the area, and if you do that correctly you should end up with something which is about 150 joules, and I think it gives you like plus or minus 10 joules there. But the important thing is you don't go down to the 0 axis, you should only go down to the atmospheric pressure, or 1 bar, or 1 times 10 to the 5 essentially. Okay, with reference to the graph, state and explain whether the rocket would have reached the same height if the air had expanded isothermally instead of adiabatically. So what happens if it's isothermal is you're going to get a less steep line on your graph. So you're going to get a gradient that's less steep, but it's still going to go from the same high pressure to the same low pressure, but it's just going to take longer to do it. So you're going to have the same pressure change, so what's going to happen is your area will increase underneath your graph, which means it's going to be higher, as essentially it's going to do more work against the force of gravity, so it ends up being higher and you get more work out of it in this case. Alright, so then on the next one we've got a diagram for a theoretical or ideal 4-stroke petrol engine or an Otto cycle. Use the figure to describe the process that occurs during each of the parts A to B, B to C, C to D, and D to A. So we've got a longer style written answer type 1 about an Otto cycle, which is very nice of them because there's so much you can say about it. Okay, so do they give us any guidance about what they want? Nope. Okay, so we're just freestyling it here. Okay, so from A to B is going to be, does it say whether it's a real or ideal? For a theoretical 4-stroke engine, alright, so we're dealing with an ideal one, so that's going to be an adiabatic compression. Which work is done on the air. On the air, and so temperature rises because you're transferring that work into internal energy. Okay, so from B to C, we've got isochoric or constant volume ignition process, but no work is done. As remember, work is P delta V, so if delta V is 0, there's not going to be any work done, but temperature rises. Because if volume is kept the same and your pressure is changing, your temperature must change as well, using your ideal gas law. Okay, then we're going to go look at C to D. So we have a look. C to D is your adiabatic expansion. For adiabatic expansion, where the air does work on the piston. The air does work on the piston, and so your temperature decreases during that section. And we've got a bit more space, so we can go from D back to A. So essentially you've got an exhaust process where there is no work done. Again using the W is P delta V equation, so there's no change in volume. So what you're going to have, so temperature has to fall because you're getting a change in pressure, again for a constant volume. Okay, so that's a detailed explanation of each of the different processes that are ongoing. Show on figure 4 how the diagram might be expected to appear if the measurements of pressure and volume made on a real engine during the process. And remember, it's a 4-stroke engine. So what we're going to get first of all, so during the working stroke, what we're going to have is it's always going to be on the inside and your corners get rounded off. So that's during the actual working stroke, but remembering it's a 4-stroke engine, so you're also going to get this process going on here. So what we've got is it goes round here, And then what it does, it goes through this exhaust and intake process, which has area as well, which represents lost energy in there. Okay, so that is this question paper complete.